Hello. So today I will talk about the dynamic properties, and then we last class we already studied about very briefly about this kind of test, and the goal of the today is that we will in detail discuss about a lot of the testing methods. So first of all, we'd like to say the Charpy impact properties and the Izod test and Hopkins bar. And then the test is like fatigue and then fracture toughness and creeps. First of all, we can say about the transition temperature in the Charpy impact test. We can do the test very simply by using there is an arm, and then we can just check that differences between the potential energy for the Charpy impact properties. But the FCC materials and the HCP materials, they have a closed packed planes. So that slip plane is not so much affected by the temperature, but for the BCC alloys, BCC structure, that they do not have that kind of the closed packed structures. So I have the examples like that, and the FCC. So FCC case. So here is there's a 111 plane. I can show you. The 111 plane is a closed packed plane, so it is very good for the slip. And the HCP case, they have the 0001, the closed packed plane. So this is, we can say, the basal plane. So this one is very effective slip plane. But in like the BCC case, it is difficult to just see that kind of the closed packed plane. So here you can see here is the 110. So the 110 plane, this plane is kind of the slip plane for the BCC case. So because of that, BCC is very affected by the temperature behaviors. So they have the good slip systems like 110 and then 112, like the 123 at the room temperature, it is fine. So in the room temperature, they have a ductile manner for the observed energy, but in the temperature decreases to the kind of the cryogenic temperatures, it goes to brittle because that slip system is not activated anymore. So usually these behaviors are just shown in the BCC crystal structures. But as I told you, so the FCC metals or the HCP does not have this kind of the distinct transition temperature. So this is the transition temperature. And impact test. So the very common impact test is the Charpy impact test. So that we can draw the pictures like that. So the specimens showed like this. And then there is a notch in here. And also, so this notch part, and then we can just put the hammer. So maybe the sample is put like this. So there is a hammer, just go to this part, and then just after the break of the sample. So they have the differences of this potential energy, so that we can check that is observed energy in the Charpy observed energy. In the brittle material, so they do not have that kind of the plastic deformation behavior, so that they just showed like this graph. But in the ductile material, they have it is plastically deformed, so that they show these behaviors. So in the toughness is so they have the notch in the Charpy impact test. So it is very easy to understand the toughness behavior. But when we want to just get the very high accuracy of the toughness, that is the fracture toughness. So the body is categorized into three groups. One thing is that the smooth body. Another thing is the notched body, like the Charpy impact properties, and the other is the cracked body. For the fracture toughness. But this is a very good way to understand the toughness briefly. So Charpy and Izod is a little bit different. So Charpy impact test, so these two parts are fixed. So, and then as I just draw the picture to you, so that back area is heated by that hammer. So maybe I just draw the pictures. I'm sorry. So I draw the pictures like this. So specimen was located like that. The hammer just hit this part, and the hammer goes this way. That is Charpy impact properties. We can get it. And then Izod test is only the one part is fixed. So it depends on the specimen's morphology or the size or the other things like that. So you can just pick Charpy impact test and Izod test. Charpy is the 10 by 10 by 55, and then Izod is 10 by 10 by 75. So it is the size is a little bit different, and then only the different thing is that the testing method. And here, so the potential energy changed. So as I told you, so the mgh, so here is h0 and here is hf. So it is just energy is different. So we just say that we got it in the Charpy absorbed energy. So we can say like that. Okay. And hardness testing is the easiest way to understand the mechanical properties of the materials, but it is not a very kind of the detailed part of kind of the test. So you can just very quickly and easily and then cheaply, and we can got some results. So nowadays, the data science is very important. So the material science, so we can get a lot of the data. For example, like when we just make a lot of the alloys, and then we need to do some tests. For example, like when we just fabricated a lot, maybe 100 or 1,000 materials. So if we can do the test like tensile test, it is very good to understand everything, but we cannot do every test. Then we say that the high throughput test is required. In that case, that a hardness testing is very important. So we can do the very shortly and cheaply, and it is easily we can understand that. So there are a lot of the type of the hardness tests. So that is the Brinell and Rockwell, and then Vickers and Knoop. These things are a little bit different. So the Brinell and Rockwell is a little bit destructive because it's a large scale, and Vickers and Knoop is a little bit small scale. So that is a non-destructive test. We can say like that. But it is just in the surface area, we can see that indent. So the indent, we can understand that what is the size of that indent, so that we can understand the hardness of the materials. So first of all, Brinell test. The ball is using the steel or tungsten carbide ball. So it is a very big size, maybe like the 10 millimeter diameter. So we just put it on the sample, and there is high load is applied, like the 500 and to the 3,000 kilogram applied to the 5 to 10 seconds. So it is a little bit long time, and then high load is applied for this part. And we can calculate just by see that here is some indent area, and then we can measure that diameter. So using that diameter of the ball, diameter of the resultant penetration, we can understand that, and then it is just calculate to the hardness. So the advantages for the Brinell test is over the large area, and then it is we don't need to consider a very small size scales when simple and use a lot of the steels and irons. Sometimes they want to show that relationship between the hardness and then the strength, but as you know, it is a not the totally, I'd like to say, but the hardness and then strength is not directly connected. So maybe we can assume that if there is a high hardness, and then maybe it is related to the high strength, but we cannot get some equations, because the hardness is only the surface condition, and then also it is a very small size. We can understand that properties of the materials, but the tensile test is overall, and then not just the small part, and then the deformation mechanism is different. It's just the hardness is only just one time, just for that surface area is resistant to penetration, but the tensile test is resistant to fracture, so it is a little bit different one. Okay. So yeah, Rockwell is the testing is a Rockwell. So the indenture is showed like that. So they also had a lot of things, and then maybe the bowl type also, and then they also had that kind of the diamond cone type. So they have a relationship between the Brinell and Rockwell. So if you have only the one hardness testing machine, maybe you can just they have a calculation. You can just change it to the numbers to the other testing methods. So that is for the superficial hardness. So it is for using usually the light loads, and useful for the thin materials compared to the Brinell test. So Rockwell is like not for like the high load, so the minor load, and then so Brinell case is the major, or the high load is allowed, and the Rockwell is for the minor load. So that is a little bit different. And Rockwell testing is limitations is not useful for that. It is under that maybe the thickness is very kind of the big deal for this part, and also the non-homogenized is not useful. But it is very easily, you can just do that, and quick and easy to use, and then just using the small indenter, and then you can just understand. And after the test, maybe you can remove or finishing it. Usually I'm conducting for the Vickers hardness. So many in the company and the industry area, they prefer sometimes a Brinell and a Rockwell case because they can understand the kind of the macro scale hardness test. But in the kind of laboratory or the schools, or we are doing that just for the research part. So we really focus on the very small size of that. Because in the microstructure, maybe they have some precipitates, and then maybe there is a different type of the grains behaviors, and we want to understand that. So because hardness test is the small one, and then they use the diamond pyramid, so that cone type is a little bit different. And there is also the Knoop microhardness test, so that they use the diamond pyramid, but it is kind of the narrow thing, the narrow way. So, and also another thing is that maybe they have the scratch. So you know already about the most hardness test. So that is maybe the diamond is the best, and sometimes there is some rock things there, and then we can use the kind of the kind of nails, and then just scratch it like that. But that is not the scientific way. But nowadays the scratch test is very good to understand, because only just push it, penetrate it. It's not you cannot get enough data. So the scratching is a very good method to understand the hardness. So this is a very good way to understand that. Okay. So that we need to consider about before the hardness test. So the location is very important. So when you conducted the test, so maybe, for example, this is a sample. Maybe this size is very small, but if you just put it so that I can just enlarge it. So if you just put it like just in the vicinity of this area, maybe they have we cannot get the exact data. So less than maybe the 2 indent diameters. So if you just conduct a test here, maybe some little bit far from this area. So that's the thing. So thickness is also important. If it is very thin, so we cannot conduct a test. So thickness is also important. And then indentation is important. So the resultant penetration size and the surface preparation is the most important part. Sometimes if you just fabricate your sample, so this is the top side, maybe we can see that if it is parallel, then we can get a very good result. And after that, so that we can get this is a very kind of the equiaxed indent, and then we can get it. But maybe sometimes you have some mistake for this part. So if it has inclined like that, maybe so you can get some different morphologies. Then in that case, that hardness value is different. So this is you need to care about the surface conditions and angles. And that is very important. And polishing the surface is very important to measure that hardness. So these are the very important part to do the hardness testing. So let's keep going on for the bending. So bending is maybe you can do many times for the like using the some kind of the wires, and you can do the bend test. And different to the tensile test. Tensile test is the one way to we just do it and do the tensile test like that. Bending is this way. So that loading direction is the perpendicular to the tensile direction. So sometimes they use that. Here is the 3-point bending test. So 3-point bending test. So here the load direction is in this area. So, but if there is a part of the crack is crack grows, then it is opened way. So mode is same as like opening mode 1. So in the bending test. So the bending test is good to understand if there is some in the surface area, and that maybe they have the layers. So then bending some direction is to understand that deformation behaviors of the materials. But bending is not very harsher like the tensile test. So the bending is I just recommend to the first time the tensile test is the best to understand that. But it depends on when you want to do the bending test. And maybe if you have an application for that bending, then maybe it can be used for that part. So bending test for the brittle materials. So here, this is 3-point bending. So 1 point, 2 point, 3-point bending. So it has the bending like that. So bending is not the harsher like the tensile test, because as I told you, so even though it is very bended, okay, I can draw a picture in detail. Bend like this. So this. Maybe I can draw the line in some neutral line. So this upper part it is compressed, and then lower part it is tensile. So here is a tension, here is the compression. So in this manner, so there is a neutral area. So in this area is for the not plastically deformed, so this is for the elastic behavior. So maybe you had experience that when you bend something, maybe it is just going back again. So we can say that phenomenon is spring back. So in the bending test, so we need to consider about the spring back, because it is not 100% deformed. In the neutral area, there is elastic deformation, so it is just elastically recovered. And shear loading is a kind of the mode of the loading, so that we can say that this one it is the same thing like the 3-point bending test like this, so that we can just use that shear loading conditions. So it is just, they have a relationship between the tension testing and then shear testing. So maybe we can use them equations for that, so to change that parameters for that. And stress concentration, it is very critical for that application and then parts for when we want to use it. There are a lot of things in the materials case we don't need to consider about sometimes, but if when we make it as a part, sometimes it has like a hole inside of that. So here, this area surrounding this hole, the stress is concentrated, or maybe things like if you make the notch, so the stress is concentrated. So the stress concentration is very important to think about in the industry part. So here is the photo like that there is screw and fasteners. So stress concentration is occurred in some valley area. So that is we need to understand this part. So stress concentration, we can say that this is the factor. Stress concentration factor is a KT. We can say that. So it's related to the type of the material, type of the morphology of the that materials and the parts. So this one is we need to consider. And sometimes, for example, like if there is a hole, it is more than like 3 times it has a stress concentration factor. So even though we just conducted the same tensile test, so this area is the pre-deformed. So we need to consider about this part. So KT, so the variety KT of the developed, so the extensive experimentation and analysis. So that is a very important part to understand. And also the fracture toughness is a very important part. So today, before I want to go to the fracture toughness, so I will explain about that type of the body. So the body. So there is 3 types of the body: smooth body, and notched, and cracked. So smooth body is usually we can understand through the tensile test. This is the dog bone type of the test specimen. So smooth area is located here inside of the gauge section. So there is nothing. It is just the kind of sometimes it is the cylinder, or sometimes it is kind of the rectangular shape. And so that is the smooth body. Notched body is usually for the Charpy or the Izod test. So this part is this part we can say the notch. So it's easy to understand. Just a very brief case of the fracture toughness. Not the fracture toughness. Sorry, just brief case of the toughness. But exactly we want to do that and then crack the body. So I will just draw the picture like this. So there is already the notch is made. An important part is that this part of the crack should be made. So this is a crack. So if it is made, crack is made, then the originally fracture toughness is starting from the very thin size of the crack. So if we want to understand the fracture toughness, then the cracked body should be made, and then fabrication of the cracked body is very important. So usually this kind of the condition that smooth body is kind of the tensile test, we can do it, and then notched body is usually. So the kind of information, kind of the example, Charpy. So cracked body is fracture toughness. Toughness. So that is the thing that we need to consider that. So let's go back to this part. So the fracture toughness. So we will talk about this part. And in the next class, we will talk about the fracture toughness test. And then we will have a chance to give you a lecture for this part in the next class. So today, we can summarize for that. We just understood about that Charpy impact properties, and then also Izod test, and also the bending test, and then a lot of tests for the hardness testing. So that is very important testing method to understand. So we need to check. We need to check that a lot of the testing method is already existed, and if you want to get some mechanical properties, you can just pick which one is better for me. And then if you just consider about the size of or the condition of your samples, and maybe you can think that in my case, a hardness test should be considered, and also in the hardness, what kind of the hardness test should be conducted. Then in that case, maybe Brinell or Rockwell, and Vickers, which one is better? So that's the point that I just explained to you about a lot of the various testing methods. So, okay, so far so good. So let's call it a day, and then in the next class I will talk about the fracture toughness again. Okay, thank you.